roots of this equation, and ideally we have two roots for this equation, and we can do it in many ways. So by forming x equal to some function, right, by x equal to some function equal to we call it, let's say, g1x, and then we start with an initial guess that could be the probable value, and then we keep on substituting the results of those values in the function that you obtain, and we find certain values. So I ask you to do it on your own. So I'll just summarize it because in this entire unit, if you will see all the methods that you will be seeing, iteration by Newton-Raphson method, or the interpolation, Lagrange Interpolation, or Newton's interpolation, all these things, it is simply nothing but just using the formula and then putting by pressing the buttons on the calculator. So that will give you the answer. But so we will see. I will summarize it quickly, not spending too much of time, because it is simply just getting the values by taking the iterations. So for this particular part, you might have received some answers which is somewhat close to 0.39 or something. I mean, I don't know the next two digits, but something near to this for this particular initial guess, if you take x not equal to 1, and if you take x not equal to 3, then for this your answer, like, I mean, if you see this is somewhere like it is your fourth iteration, and similarly over here, if you take fourth iteration, you may get it somewhere 11.415. So if you match it with your exact answers, then this is okay with your second answer. But this answer that we observed, that as you take more and more iterations, this part is actually diverging from the solution. And so it is actually diverging, it's not converging, which is somewhere here. In this case, it is converging. So we see the convergence happening in this case. The answer is getting close to this, and we also observe this by taking the graphs. So just yeah. So we see, if we see this example, then yeah. So if you see this example, so this one, x square plus the first function g1x. So in the red one, that indicates the curve that you are using as your function, and this is y equal to x. So wherever this curve is going to intersect with your function g1x, so that will be the solution, as simple as that. So you have got two solutions, one solution over here and one solution over somewhere here. And the red one, that is your guess with x not equal to 1. So we see that is approaching to this value. So that is 1, and then 0.667 and 0.411, like that. It approaches to somewhere close to the answer. But the second one, g2x, so it starts with x not equal to 3, and then it actually goes higher and higher, and it is moving away from the solution. So it is diverging. All right. Similarly, we tried with a different function, x equal to 3 minus 1 upon x, and in both the cases you might have obtained some answer. And in both the cases, again, what we are observing is that the solutions are converging for both the cases, for sure, as you take more and more convergence. So convergence is happening as you take more and more iterations, and both the values correspond to 2.618 and some more digits you can have as you go on iterating. This is, I think, third or fourth iteration. So so this also, if you visualize it by graphical way, then you would see that in both the cases it starts with, so it starts with somewhere here, and it approaches on both the sides. It is approaching your curve. All right. So it is important to see how the values are converging or diverging. And one thing which I should mention over here, which I did not mention in the last time, that what is important here in all these methods are error. You know, that is the important part, because that is for what we have been developing all these methods. You know, there are plenty of numerical methods. So the important point is here to find out the error also. So error is simply, I mean, you know this, your error is true error. True error is your true value minus approximate, or the numerical value, whatever you obtain, divided by true value. So that will give you the error. Sorry, I mean percentage. If you multiply it by 100, then it will give you the relative error. Okay, or if you don't divide it, then it's simply the error that's what you are getting. And if divide it by true value and multiply by hundreds, it will give the percentage of error. So that is what is required to be analyzed in most of all the numericals that we should be doing. Okay, so if you see in this one, of course we haven't gone beyond 3 digits or 4 digits. I haven't obtained more answers in these particular examples, but we shall see in the next examples. Okay, so that was the iteration method, and then I gave you a couple of examples that you should be doing on your own. Now in this one, you should be expecting the answers having 4 digits of accuracy. So in this case, I would expect you to find out the error also, percentage error, relative percentage error in both the case. And see that how the error percentage actually reduces as you take more and more iterations. So that means that you should be doing the iterations in these both examples until your relative error is approaching to 0%. Okay, it will take more time. It may require maybe 10 iterations, or I don't know, 12 iterations, but that you should be doing. That was with your simple fixed point iteration method. And then we saw this Newton-Raphson method, which I just briefly highlighted how it is actually obtained. So in a Newton-Raphson method, so it is a very useful method as compared to your like previous simple fixed point iteration, where you, so in iteration method, you simply iterate it with the given functions. From the given functions, you make x equal to some function. Over here, what you are doing is that you are actually approximating each point by its tangent. Each point by its tangent. So that means if you have, let me just draw some curve. If you have some curve, and at some point over here, let's say for example at this point, so you have the value of this particular function, which is f of x naught, for example, the initial value. So that is your f of x versus your curve x. And in this particular point, where if you approximate it by its tangent, okay, if I'm drawing a tangent and let's say it is making some angle theta over here, okay, and that is going to be your x naught, and this is going to be x1. Okay, this is going to be x1, this is going to be x naught. Then if you take the tangent, so that is a slope of this curve, which is simply f of x naught divided by this distance. So this distance is x naught minus x1. X naught minus x1. Okay, and tan theta is also the slope of this curve, or it is the derivative, first order derivative of the function at x naught. All right, so we have this equation, and from this you want to find out x1. So if you start with some initial guess x naught, then what should be the predicted value of x1? So that we have already written over here. X1 equal to x naught minus f of x naught divided by the f dash x naught. So if you write it in general, so that is going to be xn plus 1 is equal to xn minus f of xn divided by f prime xn. So there is a concept over here that we approximate the each point by its equivalent tangent. Okay. Now this is your x1. Okay, this is your x1 somewhere here. So again, you will take another tangent here. Okay, and that is, let's say, some value gamma. So this is going to be x2, and this is x1. So x1, x2, and that is your function f of x1. And again, you follow this same method. So you take tan gamma is equal to f of x1 divided by x2 minus x1, this distance. Sorry, x1 minus x2. So I mean, it will just repeat the same thing, and from that one can approximate. It can come closer and closer to the actual value. So for that, I gave you an example of x cubed plus x minus 1 equal to 0, and we wanted to obtain 4-digit accurate value by starting with initial x not equal to 1. All right, so I hope you might have done this, and from this simply you can find out the values. So I'm just summarizing all the values over here. X2 that you should be expecting 0.6860. X3 is equal to 0.6824, and x4 equal to 0.6823. All right, and you can go on. Acha, so you can tell me what you have obtained the 4-digit accurate value of this example. Have you obtained the same thing, or is it something different?
Same, sir.
Okay, so you obtain the same thing. So that means if you find the error, error nikali apne, just see what error you are getting. So for that you will have to first see what are the exact solutions of this answer. Okay, so find out the error and let me know what error you are getting. So first of all, you just look at this problem and find out the answers. So one short way what I can do is to simply x cube minus 1. That is your curve. So one solution that you should be getting is 1. And a simple x equal to 1. X equal to minus x cube. 0.682. Okay. So, I mean, of course, I'm not getting the 4-digit accuracy over here, but maybe you can use a calculator and see what is the 4-digit answer for this particular problem. And whatever answer you are getting, and then you see what is the error percentage, 0.6823. And if I consider it to be 0.6820, if that is the answer, then the percentage of error should be, so that is going to be equal to it will be 0.0439 percentage. It will be 0.0439 percentage if this is your exact answer, 0.6820. All right, so these are some simple examples that we should be doing. Of course, we cannot go and do all these things, but this is one more example I would like to just highlight over here. So you just do it by yourself. F of x equal to e to the power minus x minus x. Again, we want to find out the roots of this equation by Newton's method by taking the initial guess equal to 0. Okay, and we have to perform 4 iterations. So by performing 4 iterations, we shall find the exact answers as well. So your f prime x should be equal to minus of a is to minus x minus 1. And according to that, xn plus 1 should be equal to xn minus e raised to minus xn minus xn divided by, now I'll just take minus sign common out over here, e raised to minus xn plus 1. Okay, and then we just plug in the values of n. So you have n, and then you have xn over here, and I will just put one more column here that we highlight it with the percentage error as well. So for x naught, you simply start with 0. As I said, you have to start with 0. So you start with x naught equal to 0, and if you put x naught equal to 0, and if you see the roots of these equations, and now first of all you will have to see what is the exact solution for this, है ना, उसका exact solution है वो आपको देखना पड़ेगा. So I'm just writing it somewhere close to 0.56714. So I'm writing 6 digit 1 2 3 4 5 and one more digit 3. So the exact solution will be somewhere close to this. And so initially your error is actually 100%, right? Because you're guessing with initially 0. Then for second order iteration, I mean first iteration actually, because this is the initial guess. So for first iteration, so tell me the value what you are getting for 6 digits.
Point 5.
Yes, 0 0.5.
0.5.
0.5. Okay, so that means yeah, technically 1 2 3 4 5 6. And if that is the case, then we have to calculate the error. So if you simply just take it out from 0.5 up over here, so 0.067143 and divided by the actual answer. So if you estimate that, then there should be some percentage of error. So let us do that also. So what is the error? एरर निकाला आपने?
11.83.
11.83. Okay, so 11.83 percentage. So you see that it drastically reduces to this point. Okay, now the same thing if you compare it with the fixed point iteration method, the previous one, then it could have taken 2 or 3 more iterations to reach up to this much of error improvement. All right, so similarly you can do it all this. I'm not doing all this, but I just simply highlight the percentage error over here. Okay, and you have to verify on your own later on. So if you do n equal to 2, the second iteration, then the error approaches to 0.1470 percentage. This much of error you will be getting. And if you do the third iteration, then the error reduces much less than 10 to the power minus 4. Okay, it is almost 0.0000022. That is what the error you will percentage of error you will be getting in the third iteration only. So how rapidly the error converges to 0, that we can see from this method. All right, so and if you go even fourth one, then it will go to less than even 10 to minus 8. Okay, so this is important to analyze these error estimations because you know this all purpose of numerical methods is to just see the error, how the error is minimized. I'll give you a couple of examples in the assignment that you should be doing. So In the assignment, we shall be doing x sine x plus cos x equal to 0, and the initial guess is 0 pi. Okay, initial guess is pi, and second guess, second example would be f of x equal to 2x minus cos x, and the guess would be x not equal to 1. All right, and what you are expecting is to find the roots with let me just say with 6 digits of accuracy. Okay, 6D. In some book you may find it to be like 6S. They write like this also, or maybe 6S. So it simply means significant digits. Okay, I'm just writing 6D accuracy, which means what? That you keep on iterating until your error goes to 0 of the order of 10 to the power minus 6. Okay, so it may take about 4 iterations or so, the way we have seen in the previous example. So we need to find out up to 6 digit of accuracy, the numerical answer for these both equations. All right, so this you should be doing in assignment, and we should move on. So next we should be looking at is interpolation. So I'll just take a quick review of all these things, because I mean, I know you haven't done all these things and don't want to spend too much of time on this. So interpolation, and there is one more thing which is called extrapolation. So meaning of this both is simply just estimating or predicting the data from the given set of data. All right, so if you have a graph given to you, something like this, okay, and you are required to predict the data from the given set, then the way to interpolate, so that is called interpolation. If your value is to be found between the first and last point given to you, let's say A point and B point, then that is called interpolation. So if you have, let's say, these 4 digits and you are asked to find out the point over here, find out the value of this function at this point, then that is called interpolation, or somewhere here or somewhere here. But if you are going beyond this range, that means somewhere above this B, or I mean greater than B or less than A, below A or above A, if you want to estimate the value of the function f of x from the given value of x, and that is called extrapolation. And interpolation, so there are different types of interpolation. So first we shall look at one is the Lagrange interpolation. So this is something which is the interpolation by taking the linear tracing of the given data, which means, for example, if you have, so this happens only between 2 data points. All right, so if you have some, let's say, some curve, something like this, and you have given 2 data point values somewhere here, this is f naught, and somewhere here this is here f1. So in between these two, so you have these two, values x0 and x1. So you have given two data points. For x0 you have f0, and for x1 you have f1. And if you want to obtain what is somewhere in between these two, so you take the linear interpolation, taking a linear curve. So somewhere here. So your your estimated value is coming somewhere here, but actual value is here. So if you see the gap between these two, so that will be the error. This much part, ये वाला जो होगा, that will be your error. All right. So that we shall see next for Lagrange interpolation, or it is also called first order polynomial, Lagrange interpolation polynomial. This is first order Lagrange interpolation polynomial. So that is given by P1x equal to L0 x F0 x plus L1 x F1 x. Okay, and this is simply taking the difference for the 2 points. So that is, when you're taking for L0, so you take the opposite coordinate, which is x1, x minus x1, x0 minus x1 into f0, plus when you're taking the interpolated line for the first order, I mean for L1, so then you take the x0. So you take x minus x0 and x1 minus x0 f1. Okay, so this basically so this basically gives you an estimated answer between two data points. So for example, if you want to obtain the value of natural logarithmic of ln of 9.2, for example, that is what you want to find, and you are being given the value of ln of 9.0 is equal to 2.1972 and ln 9.5 is equal to 2.2513. So 2.2513, that is equal to ln 9.5 and 2.1972, that is equal to ln 9.0. Now from this you want to obtain your ln 9.2. So simply in this equation you substitute these values. So you have this, so that is your x0, let me just write here, x0 equal to 9.0, x0 is equal to 9.0 and x1 is equal to 9.5, and f0 is equal to 2.1972, f1 is equal to 2.2513. Now simply just put the values in your equation, which is x minus x1, so x minus 9.5, x0 minus x1, so 9 minus 9.5 into f0, so that is 2.1972 plus x minus x0, so x minus 9.0 and x1 minus x0, so 9.5 minus 9 into f1, which is 2.2513. Okay, simple. Now you want to obtain the value of 9.2. So your x, so at a point where you want to find the values, so that is your x. So your p1 9.2, and wherever you have x, you simply just replace it by 9.2. I think I'm not writing everything, it is simply just calculating the number. So I'm just writing directly the answer. This is going to be equal to 2.2188. ठीक है, 2.2188. Now, as I said, error is the important part over here. So if we see the actual value of ln of 9.2 by, if you take a calculator, that is going to be 2.2192. That is actual answer. So your epsilon t percentage, true error percentage, that is going to be equal to, ये कितना है, there are, so it is 0.004 divided by 2.2192 into 100%. ठीक है, so ये आप निकाल लेना, whatever it is. अच्छा, let me just do it because we shall be doing next second order polynomial, so that we can see how this error is improving. Divided by 2.2192. So this is going to be 0.0180 0.0180%. So this is the relative percentage error. Okay, now let's remember this thing, and now let us take one more data point. Okay, whatever we have taken now so far, it is simply just estimating the data between the two linear lines, है ना? So if I plot this graphically, so graphically कैसे होगा कि you have two points. So one, I mean, you have these 2 points x0 and x1, and you are getting two lines, and see, these are straight lines. If you calculate this, so this is nothing but a straight line equation वाला जो पूरा है, if you calculate this, so it is going to be something like this, L0. ठीक है, in this L1 it is going to be something like this. ठीक है, या तो फिर अपोजिट होगा, आई एम नॉट श्योर, बिकॉज इफ यू सी, अच्छा ये आई थिंक L0 होगा, बिकॉज इट इज इंक्रीजिंग, ये वाला माइनस में हो जाएगा, so this will be L1. So this is 9.0, this is 9.5, and ये वाले जो वैल्यू है, this is nothing but between 0 and 1. So in between these two, somewhere here, we are approximating the value of 9.2. So we are having a straight line, so that's why we are saying linear interpolation. Linear interpolation by taking a straight line. Okay. Now we will see quadratic interpolation. Okay, so we will see quadratic interpolation. So quadratic interpolation is also called, let's say, second order Lagrange interpolation polynomial. So quadratic interpolation simply means you are increasing one more degree of polynomial. So we are having one more degree of polynomial. P2, so P2 is equal to, so initially we had first order polynomial L0 F0 plus L1 F1. We'll add one more L2 2, and if you now plot this, all the three Lagrangian curves, L0, L1, L2, then if you are writing it for L0, then what do you take? You take x minus x1 and x minus x2, the opposite two values for x1 and x2 points, divided by, you will take x0 minus x1, x0 minus x2 into f0. ठीक है, and similarly for L1. So L1, when you are writing for L1, so you take the opposite 2 points. So x minus x0, x minus x2, and you will have x1 minus x0, x1 minus x2 into f1. And similarly, third one, so that I will act, okay, let's write down. So you will take x minus x0, x minus x1 divided by x2 minus x0 x2 minus x0, x2 minus x1. So now if you see this Lagrangian that we are taking here, all the three, so they are not in the linear form. And like if you expand this thing, तो ये क्या हो जाएगा? This is going to be x square minus of x1 plus x2 into x plus x1 x2, and divided by the whole constant term. This will be constant because when you will start with an initial guess x0, and you know these both the data point x2 x1, so this will be a constant. So whatever value you will be getting, the whole equation would be something like this. All right, so it's not a linear curve, it's not a linear line. Okay, it's a curve. So from this we will, so that's why we call it quadratic interpolation. है ना, जो यहाँ पे जो ये था, we are taking two straight lines, but now you will have third point here, but then it will not be a straight line. So that we will see in a couple of minutes by taking an example, but this is the general strategy to interpolate the data. So now we will see how to minimize this error by taking higher order polynomial of Lagrange interpolation. So we'll do the same example, but we will add one more data point. Okay, so let's do it. So we will do the same example. So I will just give you, now you do it. So ln of 9.0 is equal to 2.1972. ln of 9.5 is equal to 2.2513, and ln of 9. It's 11 point, sorry, 11. ln of 11.0, it is equal to 2.3979. 2.3979. So you have these three data points, and you want to find ln of 9.2 by taking the second order polynomial of Lagrange interpolation. Okay, so you know everything. I mean, you have all the data x0, x1, x2, and f0, f1, f2. Simply just plug in here in this equation. Okay, so you do it on your own. Let me know the answer. What answer you are getting. So I'll just finish it up over here by highlighting what you should be expecting. If you plot these Lagrangians of L0, L1, and L3, and multiplied by your functions. So multiplied by your functions F0, F1, F2, and wherever you have X, you will simply just replace it by 9.2. So that should give you the answer. Okay, and if I'll just simply write down P2 of 9.2 second order polynomial, so that answer should be equal to 2.21 2.219154. Okay, this is what you should be getting. I'm writing in 6 digit. The reason being that we want to see the error percentage. Okay, and at the moment, for a time being, like because we have been given the data only for the 4 digits, if you just approximate it by by taking the chopping of the last 2 digits, so 2.219, and because this is greater than 5, so if you have any digit which is greater than or equal to 5, you will be adding one more, so that is going to be 2.2192. Of course, this is not advisable in the way that we want to understand the error, but because we are being given the data in 4 digits, so I'm taking it in this manner at the moment. And if this is going to be the answer, then your percentage error is going to be 0%. And in the sense, if you again approximate the value of ln of 9.2 by the exact calculations in time in terms of 4 digit, then it also have the same value, 2.219. So your error is reduced to 0% almost, as compared to you had initial error of 0 point something, 0.0180, right? And that is because we are actually taking the interpolation in terms of the curve, in terms of quadratic extrapolation, interpolation. Okay, so for example, over here I have drawn all the three Lagrangians. This is L0, L1, L2, which is this. So I have just plotted the equations of all these three. So red, blue, and green. So if you see this whole curve, okay, so red, blue, and green. So it seems that all the three. So if you take the intersection, and of course they are not intersecting at any point, but what our job here is to estimate the predict the value. So you have this red, blue, and green in this region somewhere. The value of 9.2 is to be estimated, and as you keep on increasing the order of polynomial, you would see that this area gets smaller and smaller and smaller and smaller, and you should be expecting more and more accurate value. And as compared to your previous examples where we were having two linear lines, so you had only two linear lines, and from that you were interpolating the data. But now you have these quadratic curves, three curves, and with the help of these three curves, you're estimating the value of 9.2. I mean ln of 9.2. So this is the line of 9.2. So your value should be somewhere over here. All right, so that is how one can estimate the values by Lagrangian interpolation of first order, second order, or even you go for the third order also. So I'll give you one more example for the assignment, and then we'll just finish this class. So the question is, okay, let me just quickly check it in my notebook. The assignment question So yeah, just give me 10 seconds. I'll just question. Yeah, so the question is that you have to find e to the power minus 0.25 and e to the power minus 0.75 by interpolating by Lagrange interpolation of. So I'm not writing the whole thing. So find these two values by Lagrange interpolation of e raised to minus x with x naught equal to 0, x1 equal to 0.5, and so that is for this, and for this you will have x naught equal to 0.5 and x1 equal to 1. Okay, so that is the question, and you have to obtain the values up to 4 significant digit with error analysis, percentage of error. Okay, so that is the question, that you have to find these two values by taking a Lagrange interpolation of this function for x for e to the power minus 25. You take these two values, and for e to the power minus 0.75 you take these two values. Okay, so that's one example you should be doing in the assignment. So thank you for your attention and have a good day. If you have any questions, you can ask anytime. Okay, so I'll just end up over here. And yeah, just keep writing all these questions in all these answers in a proper assignment book. ठीक है, लास्ट में आपको अपलोड करना रहेगा, because we said we have a marks for this assignment also. Okay, thank you.